These are the worked solutions to the circular motion exam questions. So a lot of the questions in the previous set, the practice questions, would be typical exam questions, so the humpback bridge and the banked corner and so on. So for the exam questions, I've picked a couple of quite difficult questions. So certainly parts of these would be grade A and possibly grade A star for question 2. And I think the reason they're more difficult is because, well, obviously this is 5 marks and there's no structure. And is it a longer response? Not quite, but it's an algebraic response. So this would be certainly a grade A question here. So we've got, once again, we're looking at fairground rides. That's fairly typical. And even though this is not exactly like the conical pendulum, it's very similar. We've got a weight here, we've got a tension. So the first thing we need to do, and actually this is a really important exam tip, you need to underline this when you're reading it. We need to draw a free body diagram. So let's just reveal all of this here. So we've got the object, we can draw that if we wanted to. We've got the weight mg acting downwards, and we've got the tension, and that's it. So we certainly don't consider the air resistance. We just have these two forces acting on one of these riders sat on a chair. We could also add theta. That would be useful for our reference. I suppose if we don't include that, there might be some ambiguity about which angle we're talking about. But just that simple drawing there, the free body diagram, that gets us 2 marks. So that's an exam tip in itself. Make sure you answer the question and provide what they've asked for. So we need to consider the vertical forces. So vertically, the forces are balanced. So it's a horizontal circle. We would know, that's implied. I don't think it actually says that, but that must be implied here. So the force acting down is the weight. The force acting upwards is the vertical component of tension. So T cos theta equals mg. That's our vertical force situation. That will get you another mark. Horizontally, well, we don't have balanced forces in this case. So the horizontal component of T is T sine theta, and that provides the centripetal force mv squared over r. So already we've got 4 marks here just by a simple free body diagram and this analysis here, which is fairly typical. Certainly we've covered that in the lessons previously. So then we need to combine these two together. So if we divide the second expression by the first one, so T sine theta equals mv squared over r, we divide all of that by T cos theta over mg, and we can see that the T's are going to cancel there, and the m is going to cancel. Sine theta over cos theta gives us tan theta, and we get v squared over rg on the right hand side. Okay, so if we got that, we might get the mark for that, but we're trying to answer the question, explain why the angle to the vertical depends on the speed of rotation but not the mass. Okay, well this is the angle to the vertical, so actually yeah, they have specified that, so we would need to include theta over here. So we can see that that's equal to v squared over rg, so it depends on the speed of rotation, that's fine. It also depends on the radius, but we don't have to mention that. The key thing here is there's no value of m. So the m on the top, the m on the bottom has been cancelled. So this angle is independent of mass. So that's a fairly counterintuitive idea. You might think, well, surely the mass has an impact on the angle to which it swings. And that's not the case. We can see it algebraically. And it's also, you might have observed this in the real world context, because all these angles from the vertical would all be the same, regardless of whether the seats are occupied at all. So even if the mass of the rider is 0, if they're vacant, then they all will have the same angle. So that clear explanation of the significance of this expression would get the final 5th mark. So that's quite difficult to get all of those. So just a couple of exam tips here. So the layout of your algebra must be clear. So if this is all scribbled or doesn't progress in a logical way, then the examiner is going to struggle to give you the marks. I would also suggest you add comments to clarify. So you could say vertically, horizontally, and then explain what you're doing. So combining these together, and then certainly this final comment explaining what the algebra is telling us, the fact that the angle to the vertical is independent of the mass. So make sure it's very, very clear in terms of the structure of your answer. Question 2, part A and B are fairly straightforward. part C is the tricky one. I would say that's a grade A star. So we've got, it's always useful to underline these values in the exam, so this would be another exam tip. So we've got all these values here. We've got the velocity, we've got the radius, we've got the mass, and it says calculate the tension and the strain. So assuming that it's horizontal, well, it won't be horizontal. That's not possible. There must be a bit of an angle there in order that there's a vertical component of tension to balance the weight. But we don't need to worry about that at this stage. So this should be a straightforward 2 marks. So the tension provides the centripetal force. That's a really standard situation. So all we're doing is calculating mv squared over r, and we get 17.6. So that's a straightforward 2 marks. Part B is a little bit more tricky. So we're told the braking tension. It says find the number of revolutions per second at that value of force. Now this might have confused some students, so they may have struggled with that. But what we can find is, because we've calculated the tension here at that velocity, so let's assume that we know the tension, the braking tension, we're given that, but we don't know the velocity, then we can rearrange this to make v the subject. So now we're calculating the velocity for which the value of t is 75, and we put the numbers in. So the radius and the mass were given, so we can find that's 13.4, which is higher than the original value, so that makes sense. Okay, so that would certainly get us 1 mark, but there's 2 stages to do the second mark here. So v equals s over t, constant velocity, make t the subject, t equals s over v. S would be the circumference, 2 pi r, and we've got the velocity, so we can find the time taken for 1 complete circle. And then we're trying to find per second, so we're trying to find the frequency basically, which is 1 over t. So we could think about the formula. We looked at this, we will have done this in the waves topic, f equals 1 over t. Or you could just look at the units. So we want per second, so what do we do with seconds? We have to find the reciprocal. So it's basically 1 over your answer, and we get 1.78 s to the minus 1. It's a little bit more tricky for part B. So, but yeah, probably grade C, grade B question there. So part C is certainly the most difficult. 5 marks, possibly even 6 marks this question could be, if it's a variation. So reference to Newton's laws of motion, explain why the string will not be horizontal. Okay, we can draw a diagram. So generally speaking, if it makes that suggestion, you don't have to, but it's probably a good idea to include that to get the full marks. So let's have a look at what we've got here. So put it all on the screen there. Okay, so let's go through this bit by bit. So we've got 3 laws. So there's a lot of information here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is way more than we would need to write to get 5 marks. The mark scheme wasn't, sometimes they say a maximum of 1 or 2 for each section, but it didn't specify in this case. But we need to go through, we need to make this really clear. And the exam tip is we need to apply Newton's laws. So if you just write out Newton's laws, you probably won't get a mark. You need to apply them to the situation. So we know the first law states that objects move in a straight line unless acted on by an unbalanced force. So it is not moving in a straight line, it's moving in a circle, so there must be a force. That would get a mark. Even though it's a constant speed, the velocity is not constant because the direction is changing, the velocity is changing, so it's accelerating. So again, we're making reference to there's a force, there's an acceleration, it's not at constant velocity. So that could be a few comments there. The second law is basically F equals ma. The force is proportional to the acceleration. Well, there is a force, and that is giving it acceleration towards the center of the circle. So we can make reference to centripetal force, and the acceleration is in the same direction of the force. That is another point in Newton's second law. So again, there's a few comments there. The third law, so we need to move away from action equals reaction. That's a kind of GCSE idea. We know that if we have 2 objects, and object A exerts a force on object B, so object B exerts an equal and opposite force on object A. So we've got the we could draw the free body diagram here. We don't have to, but that might be a good idea as a reference point. So the ball is pulling the support down on this diagram to the left. So the tension is pulling to the right and upwards. So we've got this pair of forces. We've just drawn one force here. The tension is pulling the ball upwards and to the right, but from the point of view of the support in the middle, that will be pulling downwards and to the left. So again, we've made reference to the third law. And then why, let's go back to the question. So why is the string not horizontal? Okay, so it's not horizontal because if it was, then there will be no vertical component of the tension, so nothing will be able to balance the weight acting downwards. So we must have this angle, even if it's just a small, slightly less than 90 marked from the vertical, in order that we get a vertical component. And then once again, this is fairly typical to what we've seen previously. So in the vertical direction, there is equilibrium. The vertical component T cos theta is equal to mg. So we do have balanced forces there. But in the horizontal direction, there is a resultant force, a horizontal component of tension, T sine theta, provides a centripetal force. So again, we've talked that, we've explained why it must be, there must be an angle less than 90. So the object is not, the circle is not horizontal, or it's not horizontal from this reference point, in order that we have balanced forces vertically, and we have a resultant force towards the center. So a difficult question, certainly, probably A star, but there's lots of things we can write here, and quite a few of these things, certainly this last point here is very generic. We've seen this kind of comment all the way through many of the examples in this topic. Exam tip, so clear structure, maybe even little subheadings here. This idea of applying Newton's laws, not just writing them out. You probably won't get a mark for that. And then correct use of terminology. So we're talking about acceleration, not just the force, but the resultant force, components, and so on. So this is difficult and requires lots and lots of practice in order to make sure you get the full marks for this question in the exam.